So today, last lesson of this trimester. Then the next trimester, we will have the second half of the course that will be focused over design of experiments. So we will use what we have seen in these three classes, try to develop better design of experiments. Today we close the basic part related to all the theory of analysis of variance, and we will introduce also the regression analysis. You are the strongest and the bravest that survived the whole class, so I expect a lot from you. Let's move on. So what we have seen in the last class, clarification about the type of error. Now we have seen we have two different kinds of error, and they have different meanings. So we have to know from the beginning if we are looking for one kind of error or for the other kind of error. We have seen what happens when we have multiple comparison, how the error can increase, and we have to take it into consideration. And this was the explanation we have seen several times in this course to see how multiple testing can actually lead from what is supposed to be the true analysis to a completely new truth that is half false. Pardon. We have seen multiple comparison tests, how to, once the Anova analysis tells us that the factor is significant, if there are several levels in this factor and we want to know which of them are actually significant, we need to plan multiple tests on comparison to see what is actually significant and what is not. And we have introduced the two-factor project as a first step to multiple factor project that we'll see again today. And we have introduced the concept of interaction. Yes. Also, we have seen what we can do in case we don't have any repetition. We can trick the analysis saying, okay, I have no repetition, I cannot estimate my error, but if, for instance, I can assume that the interaction is null, then I can use the interaction itself as an estimator of the error. Okay, so before to move on, I show you again in SPSS, which is the tool of UPF. This is again a table with real data from one of our studies, and I'd like to show you a multiple factor analysis. We can go again in general linear model, univariate analysis. We select two factors in this case, and choose a dependent variable. We want to see how we can perform the analysis with multiple factors, and I want to show you also that we can already integrate the graph of the interactions. Again, just few clicks, and what we have described in 2 hours the previous lesson is done. What we need to see is the Anova table and understand what we are seeing here. So, actually, this is the Anova table as we have seen it in all these days. Here the study was again about stability. So we were asking the subject to stand still in different conditions, and this is the factor condition. The condition had 3 levels, so we can see here we have 2 degrees of freedom. And we were also asking them to stay in the same condition with open eyes or closed eyes. And so we had the other factor, which was eyes. So we have 2 factors, the condition and the fact that the eye can be open or closed. And so we also have the interaction between the 2. And we can see that the 2 factors were actually significant, but the interaction in this case was not. So the significance of one of the factors is this one, the significance of the other factor is this one, and then there is the significance of the interaction. We can also see, even if the 2 significant levels for eyes and condition are both very low, the 2 factors have not the same significance in our study. One has an F value of 28, the other has an F value of 161. It means that the biggest part of the variance of my study is actually related to the condition. It's not related to the eyes. They are both significant at the threshold of 5%, which is the threshold we have chosen. But one is affecting much more our study than the other. If we scroll down a bit, we see the graph of the interaction. Again, statistical tool and the software that we have available usually allow us to do all the analysis at once. But what I would do, since in the Anova table interaction is not significant, I would not watch the graph of the interaction. Now I'm showing it just to show to you this tool already integrated. And this is exactly how we have seen it in class, the previous class. In this case, we have 3 levels, so we have 3 lines for one of the factor, and the other factor only has 2 levels. Let's scroll a bit more. The other factor has 2 levels, which are closed and open eyes. So you can see how all the lines are more or less parallel. And actually, this is the result of the analysis telling that the interaction is not significantly relevant. Okay? If we had one of these lines going up in the different direction, maybe the analysis of the interaction would say, hey, there is an interaction between these 2 factors. Okay? This is just an example of what we have seen in the previous class. Now, let's play a new game. What happens when we have more than 2 factors? Okay. We begin this topic in this class, and we will close it the next trimester. We give just a hint, so an appetizer, so the next time you will also come to see the rest. We will introduce one way to see this kind of, to perform this kind of analysis with more than 2 factors, with some example, and we will introduce the concept of orthonormality, orthogonality and orthonormality, which we will see is actually one of the ways to perform multifactorial analysis. So, we have seen application with 1 factor, application with 2 factors. In the reality, we often have to deal with multiple factors. And this is a problem from several points of view. First of all, we need to see how to integrate more factors in a single analysis. As we have seen, it's not a good idea to run more monofactorial analysis because we are losing the influence of interaction. So it would be better to run just one analysis, including already all the factors. Plus, running more monofactorial analysis means doing multiple testing. So it means we also have to balance the error. If we are able to integrate all in one study, it would be much better. But there is a cost, and the main number of number of experiments we have to run. As we have said in the very first class, this grows exponentially. Because in case we have just 2 factors with 3 levels each, we have 9 combinations. If there are 3 factors with 3 levels each, we have 27 combinations, and so on. It grows very fast. Then you have to multiply maybe for the number of repetitions you want to run, and very soon it becomes prohibitive. So the idea is to try to find a way to reduce the number of experiments we need to run. And actually, we are introducing the concept of design of experiment that we will see better in the next trimester. So some examples are the Latin and Greek squares, or the project 2K and 2K minus P. This second one we will see in the next trimester. We see an application with Latin and Greek square today. So, Latin squares for 3 factors, Greek Latin square for more than for 4 factors or more. During the class, we focus on the Latin square. I will give you also the slides for the Greek Latin squares. The concept is the same, so I prefer to spend the time talking about something else, but you will have the material. We can have any number of levels, but they must be the same for each of the factors. So this kind of design of experiment requires us to balance all the factors, having all of them the same number of levels. So as we said, if we have 3 to 3, we have, so 3 factors, 3 levels each, we have 27 combinations. We can write these 27 combinations in a 3-dimensional matrix 3 by 3 by 3, or just one matrix 9 by 3. We can write all the combinations that we have in this way. Combination level 1 of factor A, level 1 of factor B, level 1 of factor C, and so on. Here are all the combinations. Since in this way to describe the combination, we have a first block in which the factor C is always at level 1, a second block which is always at level 2, and the third block in which it is always at level 3. Usually, we talk about first floor, second floor, and third floor, just nomenclature. Okay? Now, of course, it would be very interesting if instead of running 27 experiments, I would need just 9. Would be very nice. I would study a 3 factors analysis at the cost of a 2-factor one. Can I do it? Of course, the answer is yes, otherwise we will not be here. Let's see how. The idea is I can choose some of this combination wisely in order to explain the variation of the whole study. So I select only some of this combination, the ones that are in bold, and I create a new matrix. In this matrix, we have combination for factor A, B, and C, but we don't have all the combinations we have seen before, of course. We have only 1/3 of them. So what we have said before, now we can study a 3-factor design at the cost of a 2-factor design. Of course, we cannot choose these levels randomly. Neither we can choose the position of this combination randomly. They must be chosen in a balanced way. Let's see what does it mean. So all the factors have the same number of levels without limitation of them. It follows that the matrix of combination of 3 terms is necessarily square. Each factor is assessed at each level the same number of times. So all of them we have are 3 cases. And each level of each factor is combined with any other level of any other factor only once. Now, what does it mean having something balanced? Suppose that now I have a variation in one of these factors. It says, each line set a level of the factor A and present the result of each level B and C. Therefore, the difference between the averages of row identify the effect of A. We have level A1, A2, A3. If I know nothing about C and B, and I only see the averages of the rows, what is happening, the number I have here, so the averages of the row, is telling me how the factor A is changing. Okay? So now, suppose I have a variation in another factor. something happened in my experiment and level C3 change suddenly. Level C3 is present in all the line. So it will rise all the line. So it will not influence the analysis of factor A. It will neither influence the analysis of factor B because we have C3 in each of the columns only once. So we say this plan is balanced. The only analysis that will be affected will be the analysis of factor C, as it has to be. So we have a variation in C3. This is an effect of factor C. Since it is present in all the line and all the columns just once, factor B and factor A will not be affected. Imagine to have this other distribution. We have the same combination, but they are different. We have the same number of combinations, but they are different combinations. C3 now is 3 times again, but only in the third line. So if I increase the value of the combination C3, in my final analysis, I cannot know if the final result is because an augment of C3 or an augment of A3. So we say that these two factors are confused. I can see a statistical variance, but I don't know if it is because of factor A or because of factor C. Okay? So actually, having a balanced matrix allows us to avoid this kind of problem. The problem about confused effects will come again in the next trimester, because it's a bit the price to pay if we want to reduce a lot the number of combinations. Just an introduction, we will see it next trimester. All this applies with the assumption that we have no interaction. So Latin squares allow us to reduce greatly the number of combinations to test, but we must assume that we have no interaction. And this assumption is quite strong. It's not like the assumption we have done in the previous class when we were using the interaction in case of absence of repetition. Okay? We have seen in the previous class that even if we were assuming no interaction for the absence of repetitions, and then actually there was an interaction, what we were doing was to run a more conservative test. In this case, no. In this case, if actually there is interaction and we are not taking it into consideration, the final result can be wrong. So, positive aspect related to neglect the interaction. Of course, we can reduce the number of combinations. Okay? We are not interested in studying the interaction. We already know that the interactions are null. So we can focus only on the main factors, and in order to study only the main factors, we need less combination. The negative aspect is what we have already said. We must know that there are no interactions, because otherwise we can reach the wrong result. This is not such a strict assumption like it could sound. Okay? There are many applications in which we know from the beginning that the interaction is null between the factors that we are analyzing, either by the literature or because mathematically the two effects have no interaction. So it's not that strict how it could sound. Again, I don't know how many times I repeat it, first we must study the subject. We must know what we are handling with. Then we can plan an analysis. And this, it is always like this, okay? Luckily and unluckily, statistical tools are very easy to use today, so it is easy to create a table and as we have seen before, and you have the analysis. First of all, you must know how to read the output, but much more important, you must know how to run your analysis. Your statistical tool will never tell you that the analysis is wrong. It will compute and give you a result. Please.
Could you put us an example which is fair to assume?
Sorry. There is people from home, and we must talk here.
Could you put us some example of what would be a fair example of assuming no interaction between the a priori, because you have to a priori.
Yes,
kind of
it depends. It depends by your field of study. Imagine, for instance, to work with metals. You are developing some tool using different kind of metal. So one factor is the kind of metal. You have several levels. And you are doing this kind of analysis in a field of temperature that you can control. And so your second factor is temperature. But you know from the beginning that the kind of metal you are working with will not change the properties because of temperature. So you know from the beginning, from the physics of the materials that you are using, that there is no interaction between the two. Then you are measuring something else, which I don't know, and this something else might depend by the temperature. But you know that there is no interaction between the two factors that you are using. Okay, so in that case, you can run this kind of study because you know. Other things become more complex if we study in a biological field where the factors are many and very often we don't know exactly what they are and how they behave. In this case, literature can help a lot. So study the literature to see if someone else already did something similar and if they found an interaction between the factors that we are studying. Okay. So, this is our case. Now, an example, we have 3 factors which 4 level each. Here we wanted to see if the number of sold cars was related to these 3 factors: the assistance under guarantee, opening schedule, and free gadget given with the car. We have our table, and here there is the number of cars sold. There is no repetition in this case. No? We have no repetition, and we have number sold for each of the combination. Let's go back to our statistical model, okay, which is very similar to what we have already seen. We have our dependent variable. We have the real global mean. We have factors that are related to the distance between the mean and the column, or the mean and the row, or the mean and the internal factor. So actually these are related to the effect of each of the factors that we are studying. There is a factor related to the error. There are no interactions, because we have said from the beginning that in this Latin square we are not taking into consideration the interaction. So this is the kind of statistical model we are using. The deviation from the true means, of course, depend by I, j, k, which are the row, the columns, and the internal factor. We can rewrite all the model using the estimator instead of the real factors, since we cannot know the real factors. So we rewrite all this as we have seen in the other lesson, and we have the factor r, which is our error at the end. If we split the factor related to the error, we have this factor, which is actually the variance of the error we have seen in the other classes. No? Here we have the global estimation, the estimation of the global average, and each of the values. And this is an adjustment related to the row, to the column, and to the inside factor. So actually, this term has the shape of an interaction. Of course, we ignored the interaction at the beginning, but inside the model they will appear somewhere, and they appear inside our error. So in absence of interaction, so we suppose null interactions, it can be said that this term is non-zero only for the effect of the error, which is this part. So if I can assume that all this does not exist, so what I have is this one, which is the estimation of my error, which is the experimental uncertainty. Performing the square and summing, we go back to what we have seen in all the other classes, the total sum of square of our experiment, the sum of square between the row, which is related to one of the factors, the sum of square between the column, which is related to the second factor, the sum of square inside the factors. We finish the dimension, so we are inside the factor, and the sum of square within, or the sum of square of the error. The degree of freedom of each of the factors are equal to the number of levels minus 1, as we have already seen in the previous classes. The total degree of freedom are given by the number of all the experimental data minus 1. So we can obtain the degree of freedom of error by difference, and we obtain this. We can write our Anova table. So we go back always to the same. We have our Anova table, we have the row, columns, inside factor, error, and the total of the sum of square. We have the degree of freedom, we can compute the mean sum of square. Simply dividing the sum of square by the degrees of freedom. This is something we have already seen, no? We have, for each of them, for each of the factors, we have expected values. So we know that each of the factors should have a variance. Now we are talking about variance. This is the mean square. This is supposed to be the variance of the factor plus the variance of the error. No? The error is always present. Here we have the variance of the error alone, so we can identify the variance of each single factor. So we go back, computing our Fisher coefficient, simply dividing the mean square of each of the factors by the mean square of the error. If the mean square of the factor is much bigger than the mean square of the error, then this factor is significant. Much bigger, how much bigger? We have seen it depends by the percentage of error we are ready to accept. So in this case, we have this table. We compute the Fisher coefficient. Looking at the tables from the Fisher coefficient, we can obtain the p-value, looking at the table or asking the PC. In this case, if we assume an error alpha 5%, none of the factor is significant. I add again this line to remember that 5% is just something that we choose. Okay? It's not golden rule, it's not written in the sky. For a kind of study, a significant value of 10% might be more than enough, and in that case, we have one factor which is significant. Even if we still want to keep the error fixed at 5%, we have some more information saying, okay, none of them is statistically significant, but one has more related variance than others. So maybe this variance is still just related to error, but is bigger than the other two. Okay? And again, it is reasonable to compare, even if we don't have a statistical comparison, but it is reasonable to compare and saying, okay, suppose I'm not sure if I want to keep an error of 5% or an error of 10%, but for sure, schedule is not affecting my study, because the Fisher coefficient is really small, much smaller than the other two. Oh, this was one block. We will see in the next trimester other kind of design of experiment that can allow to reduce the number of combinations, and we will see that they have other advantages and other disadvantages. Okay, this is just a beginning. We introduce the concept of orthogonality that will allow us to do something very interesting, which is decompose one factor in more questions. Each of these questions might be a factor itself. So we will see that this is the basis to run a multifactorial analysis without, well, with few limitations about the number of factors. More interesting, and this is something that usually is not implemented in the software, so it's something that you have to do it by yourself manually, but it is very interesting. You can choose specific questions within your analysis and use this tool to answer that question. We will see how. So stepping back, we studied the single factor analysis of variance and showed how one can investigate differences in between the columns. It was shown how the test 2 by 2 may lead to inconsistencies, what we have said before. No? We cannot just run multiple monofactorial analysis. And how it can heavily increase the probability of error. So another method to investigate the effect of a factor is to decompose the sum of squares between the columns in C minus 1 component, as many as the degree of freedom. So suppose we have 5 levels in our study. We run an Anova analysis. We find out that this factor is significant. We don't know which level is bigger than the other. We need to run a post hoc analysis. But post hoc analysis means multiple comparisons. We can choose some post hoc analysis that can reduce the error, but in any case, we have to run multiple comparisons. What it is suggested here is that instead of running multiple comparisons, we can choose a number of questions which must be not more than the degree of freedom that we have, and decompose the total sum of square of this factor in sum of the sum of square of each of the questions. Very confused, let's move on, will be clear. Each of the C minus 1 contribution corresponds to a question, to which give an answer by statistical test. So if we have 4 levels, we can answer 3 questions. We cannot answer infinite questions, so we must choose questions wisely. This is a rule for life. As will be seen, the formulation of a question is equivalent to writing a linear combination between averages of the scores. What does it mean? So if any question is orthogonal to the other, and we go back to the title, orthogonality, then we can apply the following properties. Each question is independent from the other, and it is interesting how the chances of making error of type 1 or 2 during each test are independent to each other. The C minus 1 contribution, also the sum of square, are decomposition of the sum of square of the total factor. So the sum of each of the sum of squares of each of the question must be equal to the sum of square of the factor we are studying. It's like saying, suppose we have a factor that we are studying, any factor. At the beginning, we were looking at the lifetime of the batteries. No? The factor was the brand of the batteries. And we had several brands with several values. We have a total variance in our experiment. This total variance is related to the error and the only factor we are studying. Okay? If now we say we had 4 different brands, to what we have said, we can split this factor in 3 questions. 4 brands, 3 degrees of freedom, 3 questions. Each question, that will be a mathematical question we will see later, will have a sum of square. The sum of the 3 sum of square must be, again, the total sum of square of our study. So the variation, the total amount of variance of our study will not change, will be divided into the 3 questions that we have. As already described, its sum of square between the columns can be decomposed in C minus 1 sum of square, as many as the degree of freedom. Each sum of square corresponds to a linear combination of columns. So given the question, on the basis of this, we can construct, with suitable criteria, linear combination, and from this can be calculated the sum of square. So we are actually creating a new table that allows us to compute new sum of squares that we know how to compare. Okay? We already know that if we have a sum of square of a factor and we have a sum of square of the error, then we can compute an analysis and we can see if this factor is significant or not. So what we can do is create new sum of squares starting from the data that we have. And this sum of square must be related specifically to the question I have. I can always do it. What I have to do is to create it in a wise way that must be related to orthogonality, which is this. So, suppose now we have just these j levels. Okay, so we write, this would be the estimator of the columns. You remember the nomenclature, how it was done, no? The point stands for the things that are changing, so are the repetition, and j would be the single column. So if we have 4 levels, we have 4 columns. And we know, as we have said previously, if we have 4 levels, we can create 3 new factors. 1, 2, 3. And we can assume that there will be the sum of the value we have plus a coefficient that we have to define. So we can build this new vector starting from the 4 level we have, combining it with a matrix of factors that we have to define. So actually, we can write it in this way. So what we need to know is this matrix in order to pass from these values to these values. This matrix must be an expression, a mathematical expression of the question we want to answer. So, as we said, this matrix that we want to build must fulfill 3 rules. In order for all we have said to have a meaning, these 3 rules must be fulfilled. First, orthogonality. Second, orthonormality. And third, balanced question from the mathematical point of view. Let's go seeing each of them. Orthogonality. If 2 vectors are orthogonal, means that the scalar product between each row vector of the matrix of the coefficient is 0. We can create coefficients that fulfill this. So the scalar product between this coefficient is 0. In general, we can write it like this. Orthonormality. So each row vector of the matrix or coefficient should have unitary norm. The norm of the vector is typically given by the root square of the scalar product of the vector itself. Generally, this is not very difficult to achieve. If we have orthogonal vectors, we can just divide them by the norm, and we have orthonormal vectors. Balanced from the mathematical point of view means that the sum of the coefficient must be 0. Well, as we said, of these three rules, the first and the third are essential. The second one, related to orthonormality, it is always true if the matrix is orthogonal, then it is easy to apply normalization. So this, for instance, is a matrix that can fulfill the request that we have seen before. So we can use this matrix to compute the three components that we have seen before. Verify the three properties. It is orthogonal because the scalar product is 0 for each of the factors. It is orthonormal because the norm is equal to 1. And it is balanced because the sum is equal to 0. So it means we can use it to create three new factors starting from one factor. So suppose now we have these values with a number of 4 repetitions, we can build this matrix. So these are the 4 values of the 4 levels we have in our study. This is the matrix that we just used. These are the new components. Using these new components, multiply them by the repetition that we have, we can compute the new sum of squares. Their sum, and the sum of the 3 will be equal to the sum of square of the total analysis with one factor. So we have seen how to apply these 3 assumptions in order to create a matrix that can be used to decompose our sum of square into 3 different sum of square. But we need to create a matrix that has a meaning, okay? Because we said at the beginning what we want is to answer questions. So let's see an example. Suppose it was performed a statistical analysis to assess the impact of different drugs on the relief of people suffering from headaches. Okay? Has been performed a monofactorial ANOVA with X medicine, 4 different types. So we have one factor, which is the medicine, 4 different levels. And we measure the reduced pain, 1, no effect, 15, disappearance of the disorder. 8 people were administered with the 4 medicine, so we have a repetition equal to 8. And we have the 4 medicine, placebo. So actually there was no medicine. Aspirin type 1, aspirin type 2, and Orudis, another kind of drug. We run our ANOVA analysis, monofactorial, because we have only one factor, and we see, yes, the medicine has a strong effect. Okay? So different levels of our study have different results. The factor medicine is statistically relevant. Now we need to know which one is really interesting. If we are interested in all the combination possible, then we have to run the post hoc analysis as we have seen in the previous classes. But often we are not. We are actually interested only in specific analysis. So we can create a number of questions. In this case, we have 3 degrees of freedom. We are allowed to choose 3 questions. We have 3 wishes to use. Let's see how to choose them wisely. So we reject H0, the drug actually works, and we want to answer the question. Which are the questions? First question, is placebo actually different from the other drugs? This might be one question we want to study. No? Sometimes we have some studies in which the placebo works like the medicine. So we want to see if the placebo is actually different. Focus on this. It says, is placebo actually different from the other drugs together? It means I'm not going to analyze in this step each of the drugs independently. I have from one side placebo, from the other side the drugs. Second question, does exist any difference between the 2 aspirins? Because maybe I'm interested to see if 2 aspirins, which comes with different names and different costs, are actually different or not. If they are not, I will use the cheapest one. Third question, does exist any difference between Orudis, which was the other drug, and the 2 aspirin together? So I'm not, again, here doing any difference between the 2 aspirin. I'm pulling them together. Remember that every question we are trying to do is going back to sum of squares. It's going back to an analysis of variance. See if the placebo actually is different from the other drug together means, is the variance of my study related to the placebo bigger or smaller statistically than the variance of the other drugs? Is the variance related to one of the 2 aspirins bigger or smaller or different from the variance of the other drug, of the other aspirin, and so on? So we want to create a matrix that can represent these questions. Must be linear combination among the means of the columns. So to compare placebo, for instance, with the other 3 drugs together is the same as subtract from the mean of placebo the means of the other 3. To compare the 2 aspirin, this is easy. It's just to subtract one from the other. If the result is statistically not different from 0, it means that the 2 are not different. So we can build this table. So the first row answered the first column, answered the first question. Placebo, to placebo, I'm giving a value 1 because I'm analyzing placebo altogether. Is this different from the other 3 drugs together? So I'm giving 1/3 to each of the drugs. Placebo is negative and the other 3 are positive. So the line is balanced. I'm actually subtracting one to the other. Second row, I'm analyzing the 2 aspirins. I'm looking only at the aspirins. So I'm giving 0 to placebo, 0 to Orudis, -1 and 1. Last row, I'm comparing the 2 aspirins with Orudis. I'm not using placebo. I'm putting 0 here under placebo. The 2 aspirins for me have the same weight, so I'm giving -half and 1 to Orudis. I'm creating a matrix which is a mathematical representation of my questions. Now I need this matrix to be orthogonal, orthonormal, and balanced. If I can do this, I can use this matrix inside my analysis. this is what we were saying before. No? There was no point in subtracting from the mean of the placebo the average of each of the other three. It would have been 1 minus 1 minus 1 minus 1. It would have been not balanced, so we cannot use it. The idea is that it must be balanced. Rule of orthogonality and balance are actually respected. It's not respected the rule of orthonormality, so we have to normalize our data. We compute the norm for the three vectors, and we divide by the norm. So we can compute the zeta values. And with the zeta values, the sum of squares related to each of the questions that we were analyzing. So we can write a new Anova table, in which we have the factor medicine, which is now split in three new factors, because we have three new questions. We have a total sum of squares related to the medicine, which is now split in three different sum of squares, the sum of which is the same. We have 3 degrees of freedoms. We still have 3 degrees of freedom. Each question has 1 degree of freedom. We have mean squares that now are equal to the sum of squares because the degree of freedom is 1, so we always have this, the sum of squares divided 1, and we have the same number. We can compute the Fisher coefficient, and we run the analysis this way. And we see here the answer to our questions. Placebo is different from the other drugs. The two aspirin are not different between each other. The aspirin are different from Orudis. So we used Anova analysis, we used a comparison of the mean squares to answer the questions that we had at the beginning. Of course, instead of this kind of question, we can create new factors. And we will see in the next trimester how we can create multifactorial analysis starting from this idea.
Excuse me, P here means?
The placebo versus all the rest that is not placebo.
I thought you choose placebo with placebo.
No. So the first and the third case are significant, while the second is not. As we have said, we can look at the p-value, but we can also look at the variance and see how much of my study is depending from one thing or the other. In this case, looking at the variance, the total variance of our study, is giving an idea of what is happening. No? Is the variance related to the question one aspirin versus the other aspirin? So it's a very small variance. It's really not affecting the whole study. Probably because the two aspirin are very similar. So once I subtract one to the other, it's going close to 0. The biggest variance is given to the difference between the two aspirin and Orudis. So actually, if we want, the average effect of the drugs compared to placebo gives a difference which is smaller than the difference between Orudis and the two aspirins. Of course, we have to do some assumption here, okay? Here we are averaging all the three medicines to answer this kind of question. Is it reasonable to pool all the medicine together? Maybe yes, maybe no. We can design a multiple step analysis that can allow us to see if it is reasonable or not to pull together more factors, more levels or not. For instance, a part of analysis is telling me that the two aspirins are not different to each other. So it is different to pull the two aspirin together in order to compare them to Rudis, because actually they are not statistically different one each other. This part of analysis maybe is less solid because I'm pulling together three medicine, which actually in the other side of analysis I'm showing that they are not the same. But okay, as an example, I think this is important to show that there are different approaches to look at the data. We must not stop looking at the p-value. Okay, the p-value can be for all of them smaller than 5%, but then each factor can have different weight. Well, this, we already commented this. Now, the boring part is over. Well, there is another less boring part later, but let's say all the part related to design of experiment. Please tell me. We have.
Is something related to the Latin square? So before.
Yes, please.
How is this different from computing in this experiment? For example, comparing the effect of placebo against all the other medicines. How is this method different from comparing the effect, or if you prefer, could I use these Latin squares to see the effect of placebo
Okay.
against all the rest of the medicines?
Yes and no. I explain. The method of orthogonality is not related to the use of the Latin squares themselves. So the idea to use orthogonality to create your own matrix to answer your own questions cannot be directly applied to the Latin square. But you can choose your factors. So you can choose your factor at the beginning in order for the factors to represent part of your questions. This can be done. So we have two levels in which we can work. One is at the very, very beginning, which actually I think is the best way to work. So before to start any kind of analysis, already create your factors in order for them to answer your questions. You want to see the difference between two aspirin, you create one factor which is the difference between the two aspirin. So you have the value of one aspirin, you have the value of another aspirin, and this is what the company is passing you. You compute a new table, a new column, which is the difference between the two, and then you work with this one. And this will be your factor B. This can always be done. Orthogonality allows us to do another step and say, okay, I have to work with one factor because this is the main factor I want to work with. But then, in a second way, allow me a bit of flexibility without completely changing the design of experiment. I can use this value to answer other questions. Personally, I think it is always better to start very clearly from the beginning with the things that you want to analyze. But of course, sometimes it's not possible. And also, being very rigid in what you have designed is not a good idea neither. So having the possibility to be a bit flexible sometimes is useful. So I want to show you a small practical example on how to use design of experiment in the implementation of a power analysis. We talked about power analysis in the previous class. We are not going through this, but the idea is I want to know how many repetitions I need in order to have a good experiment. And we have seen this is related to the type 2 error, so to our beta value, to the power of our test. And this was an actual example of a student coming to me asking to run a study using this kind of device. This device is used for rehabilitation. We have subject with an injury of the knee, and this device is moving the leg of the subject. the actual procedure is usually performed by a physiotherapist, which cannot stay with you all time long. It is usually the golden standard. It is usually much better than using the device, but you have the physiotherapist, if you are lucky, 1 hour a day or 1 hour a week. This machine can be used more time. Is it better? Is it comparable? So this was the kind of study. And actually, they were doing one-way ANOVA with 3 levels. So there was the manual therapy, there was the standard device that you can find that you can buy, and there was a new device that they were trying to develop. And the idea was how many tests I have to do in order to verify if my new device is better than the new one, than the old one, or at least if it is comparable with the manual therapy. They were measuring 8 dependent variables, which I don't remember, but okay. They were related to the angle of the knee, the speed of the that can be applied in order for this knee to move, etc. And they already had a preliminary analysis over 5 patients. So they had some value. This can be enough to run a power analysis. This tool is called G-Power, is free. You can download it for free, and I suggest you to do it. It's very interesting and allow you to run power analysis using different tests. What you have to do is choose the test family here on the left. They were running an ANOVA with one factor, so the test family is a Fisher test. Once you choose the test family, it allows you to choose different kind of statistical tests. In this case, was one-way ANOVA, so we selected one-way ANOVA. Once you choose this, you can run the type of power analysis that you need. In our case, was a priori. So knowing that I want to keep an alpha value and a beta value, how many subjects I need. So it asks the level of the alpha error, the level of the power, the number of groups, and what is called the effect size. We are not going through what is the effect size, but let's say it is related to the variance that you have. So you need some information about your variance. That's why it is very useful to have some preliminary analysis. So they had repetition over 5 subjects, and one of the measurements they were taking, that was the degree, I think, was 73, 50, 70 for these 3 groups. They found out with this situation that they need 63 subjects. That's the result of the power analysis. If you want this alpha error, this power level, knowing that your distribution will be more or less this, you will need 63 subjects. Of course, the knowledge related to the distribution can make a lot of difference. If you have previous data computed in a completely different way, so they are not representative of what you are going to do, power analysis will give you a number, but it doesn't mean this number will be a good one. Then there was a second problem. This is the test for one dependent variable, but they wanted to measure 8. So you need to correct the error. And from 0.05 became 0.006. If I still want a power of 0.8, now I need 99 subjects, which for them was too much. So at the end, they just decided to use only 2 dependent variables for the study, which means using an error of 0.025, which meant for them that 75 subjects were enough. Questions? So this was an example of how to use all the knowledge that we have seen during this course to prepare a power analysis. So to start from the beginning knowing how many repetitions I need if I want to measure this thing. Of course, we need previous knowledge that must come from previous analysis or from the literature or from some mathematical analysis that we have done. Somehow we need to know what we want to measure. Okay? Let's take a break and then we come back in 10 minutes. Okay? See you later. With the last part of the course, which is focused on simple linear regression. Now, at the very beginning, we have said that we have generally two different approaches. We will see later a bit more. But very often we can be unsure whether it is better for analyzing our data linear regression or comparison of means. Sometimes it seems obvious that we prefer something, but we forget or we don't know that the underlying theory is actually the same. So very often, something that seems mandatory to be analyzed in a way might be better to be analyzed in a different way. Usually, it is interesting to have simple linear regression, or in general linear regression or regression, when we want an equation that allows us to predict something. We just don't want to see a difference, but we want to predict an actual value. So starting from set of values that we have, we want to create a law that allows us to predict the missing values. This usually should be the reason why to use linear regression. But let's see a bit what are we talking about. So, as we said, regression analysis is used primarily to model causality and provide prediction. Model causality. We have seen in the very beginning that actually there is no test that allow us to verify causality. We can verify a regression between the two. We can verify that there is a law that is binding the two events. Correlation. But we cannot test for causality. We must know if what we are seeing is causality or no. We have seen in the first slides that there was a regression of 99 point something % between the consumption of margarine and the number of divorce. Okay? The regression was huge. Unless margarine is developing something at the biochemical level, there is no reason for this regression actually to have causality. But the idea of regression is this one. So I have one factor. I know that somehow this factor influences another factor. So I want to model this causality. I am the one who knows that there is causality. It's not the test that is telling me that there is causality. So I want to predict values of a dependent response variable based on values of at least one independent variable. We want to explain the effect of independent variables on the dependent variable. Said like this is pretty similar to what we have seen for ANOVA. We have dependent and an independent variable, and we want to see the effect of one over the other. And we can have different kind of relationship. Here we have a linear positive relationship, a relationship which is not linear but still is present, a negative relationship, no relationship. Okay? Each of them can be a different kind of model. So we have, in the case of simple linear regression, the relationship between the variables is described by a linear function. It means that the change of one variable, of course, causes the variance of the other and dependency of one variable of the other. We have an equation, which is the linear equation, which I think everybody knows. We have the dependent value. We have a factor beta 0, which is the intersection. We have the slope, which is related to our independent variable. We have the error. Well, dependent response, and these are what we have said. This is the conditional mean. So it means, what is the average value of y given this value of x is given by this. And this is the idea of prediction. So I have some fixed values of x, which come from my experiment. I create a regression, so I come out with this formula. Now I can compute any kind of value of y, just switching the value of x at the value that I want. Okay? If I have a good regression, I can do it. So suppose these are the observed value, and I want to create this regression. I plot this line. This value, the distance from 0 here in y is my beta 0. This value, the slope, is my beta 1. The regression is the conditional mean. The actual distance between the conditional mean and the real value that we have is our random error. So, well, this is what we have commented. As it happened for the Anova analysis, for the regression analysis the same. We have a real value that we don't know, so we try to estimate them. So we have a real slope that we will never know, and an estimated one. And we can estimate beta 0 and beta 1 using B0 and B1, using again minimizing the sum of the squares of the residuals. All the errors that we have for our measurement compared to the regression that we find, we try to minimize these errors, so we change the slope until we find the minimum of this sum of residuals, sum of square of residuals. So we can find ourselves in this situation in which there is a real regression that we don't know, and there is the regression that we can compute. The estimator of beta 0, which is B0, the estimator of the conditional mean, the estimator of the slope, the estimator of the error, which is the residual. Okay? Similarly to what we have seen for the analysis of variance, we have a set of values which are real and which we cannot measure directly, so we have to estimate them. And we can work with the estimation. So the intercept is the conditional mean of y when x is equal to 0, while beta 1 is the variation of conditional mean of y related to a variation of x. We can estimate them using this estimator for the intercept and this estimator for the slope. Going a bit fast over it because I think it's not really difficult nor important. Again, the aim of this part of the presentation is not to explain every mathematical detail, it's more to give you the tools to understand if a work that you read is properly done or not, you can trust it or not, and when you do your job, to understand if you are really doing the things properly or not. Let's see an example. So you wish to examine the linear dependency of the annual sales of store on their size in square footage. So you have stores that are bigger or smaller, and you want to compare the dimension of the store with the number of sales. You have a number of stores, square feet, annual sales. You compute, you plot the points, no? Square feet, annual sales. Using this distribution, you can compute your regression. Okay? You can compute your regression, and you see that your estimator of the intercept is this one, and we have it here. Your estimator of the slope, B1, is this one, and we have it here. And we can write this regression. Is it a nice regression? Can we trust it? Yes? No? Let's see if we can find some tool that can help us understand if this regression is good or not. So this formula like this is telling that the slope of 1.4 means that each increase of 1 unit in x can predict an average increase of y. So an average increase of x means that y is increasing of 1.4, 1.5. This is what the equation is telling us. First of all, switch on the brain. Even if this is true, we know that must be a limit. So it's not that if I have a store that is a country big, it will have sales that will increase constantly linearly. Okay? So first of all, even if it is true, knowing the topic, we know that it will be true in the range that we are analyzing. Outside this range, things can be different. This is a general error. To extrapolate something outside of the analyzed range. I have a regression line, so it is a line. I can compute even outside of what I have measured. Mathematically, yes. Practically, you don't know what will happen outside. The rule that you have found, if it is correct for the range you have used. So first limitation. So the estimation is that for each square foot in the size of store, the expected annual sales are predicted to increase of $1,400 per square foot, a golden foot. Let's go back to our friends, the sum of squares. We know that we must have something like this. We will have a total sum of square, which is our study, and this sum of square must be split into a part which is related to the error and the part which is related to the model that we are using. So we have the total sample variability, explained variability plus unexplained variability. It reminds something, no? So we see that we are going in the same direction. Total sum of square measure the variation of all the values that we have compared to the global mean. Sum of square of the regression explain the variation attributable to the relationship between x and y. Sum of square of the error is the variation attributable to the factors that are not the relation that we have already found. Again, here is the same as with the analysis of variance. Everything that we are not taking into consideration is going inside the error. So suppose this is our slope, and this is the actual value. This is the total variation of our experiment. This is the variation which is explained by our regression, and this is the variation which is related to the error. in this specific case, the variation related to the error is bigger than the variation related to the regression that we have chosen. So if these are all the data that we have, probably this regression is not really significant. But we have to do the sum of the squares. So we are going to compute all these values for all the data that we have. And ta-da! We have again an Anova table. So the simple fact that we have an Anova table in the regression line, it should suggest us that we are somehow using the same tools. Just we are using them in a different way. And we have, again, one factor, which is the regression, and the residuals, which are our error. And again, we have the degree of freedoms, we can compute the mean square, we can compute the Fisher coefficient, and from the Fisher coefficient, the p-value. And we have this sum of square. We see that is strongly significant. The p-value is very low, and the Fisher coefficient is very high. These are the data related to the first graph that we have seen. So, looking at the Anova table, I would say, yes, this regression is significant. Is it enough? Of course, no, otherwise the course will be over now. But let's see. So we have the degrees of freedom. The regression has 1 degree of freedom. The residuals are the other, so the total degree of freedom minus the degree of freedom of the regression. Sum of squares of the error of the regression, total sum of square. We can compute what is called the coefficient of determination, the R square that everybody looks for in a regression, which simply is the ratio between the sum of square of the regression and the total sum of square. Clearly, if all the variance of my experiment is explained by the regression, it means the error is very, very small, so this R square will be very close to 1. It means that my model is explaining the distribution very well. Well, this is what we have said. And here we have some example. No? 3 points perfectly in line, R square 1. R plus 1. R, which is simple, the root mean square of R square. You must pay attention when you read the paper. Be sure that what you are looking for is R or R square, because an R square of 0.7, okay, might be nice, and R of 0.7 is definitely worse. So take this into consideration. It is nice sometimes to work with R because it also tells you the direction of the slope, if it is positive or negative. So you have this kind of advantage using one and using the other. Of course, while you have no regression, your R square and R are equal to 0. Here is an example. Of course, if R is 0.9, which seems almost perfect, actually squaring 0.9 becomes 0.81. So it decreases quite a lot. And here, if you have 0.7, it decreases more. So, standard error of the estimation. We can see the standard error of our slope looking at the sum of square of the error related to the number, to the sample size, and to the number of independent variables in the model. It somehow defines the standard deviation of the variation of the observation around the regression equation, a lot of Asian. So these are interesting values to keep into consideration when you look at the regression. The R-square and the standard error, okay? This is telling us that 95% of the variation in annual sales can be explained by the variability in size of the store as measured by square footage, okay? But we have to take into consideration this. Normality is a ghost that is always present when we are working with parametric analysis. All the things that we have seen are true if we have normality. What does it mean? Y values are normally distributed for each x, and the probability distribution of the error is normal. Then we need homoscedasticity. The variance must be constant. The errors must be independent. This is very similar to what we have seen for ANOVA. What if not? Behold the data sour. These two regressions mathematically are the same. It is quite clear that they are not. But if you publish just the number, these two are the same. Here, these two distributions have the same coefficient, which is pretty high, a Pearson correlation of plus 0.81. But actually, if you take into consideration this pattern, then you see that the C image is not one regression, but are 5 different negative regressions. But these two have the same Pearson coefficient. It is always important to take a look at the data, to watch your distribution, to understand what we are working with. That is the very big problem that we have with machine learning, with working with big data. So when we have too many things and we really cannot look at it, and we sometimes make the mistake to use the tool as a black box, put everything inside and look at what is coming outside. And as we have mentioned in the first class, this actually is leading to problems in science in general. We have to find a balance. Sometimes we are forced to use hundreds of thousands of variables. We cannot plot all of them. And even if we can, sometimes it's not really useful. So we have to find other ways. But at least when we can, we must look at the data. Especially when we are working with linear regression, look the distribution sometimes is much more useful than verifying his statistically significance or not. Variation of the error around the regression line. So suppose now we are in 3D, and suppose this is our regression line, the error must be distributed normally around the regression line. In order to do this, we can perform the analysis of the residuals. So we look at the error, and we see if this error is distributed in a proper way. We want to verify that we have linearity and evaluate violation of this assumption. Actually, one of the best ways to do this kind of analysis is graphically, not performing a test, look at the data. These are the distribution of one set of data, and this is the resulting regression. If we plot, it is already quite visible here, but if we plot the residuals, so our regression becomes a straight line, and we plot only the variation of each point from the straight line, we see that this is not linear. So finally, we can compute a regression, linear regression, but this linear regression is not really representative of my data. Here, yes. there is a variation, because of course there is an error, but this variation is linear and constant all over my regression. Here probably I have another kind of regression, but for sure it's not a linear one. Using a linear regression in this kind of distribution to predict value clearly introduce quite a lot of error. More importantly, it gives really a bad meaning to your analysis. You are telling that something is linear when actually it is not. If you have enough points, the R square here can be pretty high. But still, this is not a linear regression. You can be more, how to say, honest with yourself and with the readers of your paper, maybe splitting the analysis in two and say, okay, I have two linear regressions. I can approximate it. I know that the distribution is not linear, but if I split it in two, then my linear approximation has more meaning. This can be a solution if you don't want to handle exponential regressions. Again, no? Heteroskedasticity. Here, the error is not constant along your distribution. You have very small error here and huge error at the end. It is not constant. Here, you have homoskedasticity. This regression is not a good one. If we go back to the data at the beginning that they had so significant regression and actually also high regression, and we plot the residuals, well, they are not pretty constant, no? There are these 3 points that are going this direction, then the lower part maybe is a bit better, but first of all, we have very few points, but okay, it is an example. But you can see that even if we had a high R square, this R square was statistically significant, I would not use this regression line. This analysis comes before the analysis of the statistical significance of the slope. If the residuals are not good, don't use regression. Purpose of correlation analysis. As we said, correlation analysis is used to measure strength of association between two numerical variables, can be used to predict. And this is what we were commenting at the beginning. The strength of the correlation, of the relationship, is measured, not the causal effect. This cannot be measured. This is about us. We must know, knowing the topic, if one thing depends to the other or not. The population correlation ρ is used to measure the strength between the variables. Sample correlation coefficient R is an estimation of ρ. And it is used to measure the strength of linear relationship in the observed variables. So this is what we have seen before. No? We have this, several examples. Lacking an awareness of the assumption underlying least square regression is one of the pitfalls of regression analysis. Again, now compute a regression analysis is extremely easy. You can find tools that can compute this regression everywhere. You use it, you have your regression. You don't care about how and why these are the results. Very bad approach, okay? Because we can find something that seems really relevant, but actually is not. Tomorrow, you already have your law, you trust, and you want to use it for another study, it will not work. Because somehow it was working only in that case because you had poor regression. Not knowing how to evaluate the assumption is another pitfall. Not knowing what the alternatives to least square regression are if particular assumption is violated. Using a regression model without knowledge of the subject matter. That's why I can help you revising your model if you want. I'm always available. I cannot tell you if this is correct for your field of study, because I don't know. I know the tools. I can tell you if the tool it is used properly in the meaning of the use of the tool, but I don't know if the values that you are putting inside the tools are proper or not. This, you must know it. Strategy for avoiding the pitfalls of regression. It is always a good idea to start with a scatter plot and observe. As we said before, no tests, no numbers. Let's look at the data, how they are distributed. Are we talking about one regression? Are we talking about two regressions, linear regression, curve regression, polynomial regressions? Another very typical error is to have a group of points here, a group of points here, regression 99. Of course, between 2 points there is one line passing, but this is not a good regression. Perform residuals analysis to check the assumption and use histogram or stem and leaf display, box and Willis in order to verify the distribution of the residuals and verify if the residuals are actually constant and linear and if you have homoscedasticity in your data. If there is violation of any assumption, use alternative methods. Nobody usually forces you to use regression. You see that your distribution of the error is not good enough, your distribution is not linear, you cannot use a linear regression, well, we go back to the analysis of the means and we use analysis of variance. If there is no evidence of assumption violation, then test for significance of the regression coefficient. If we see that actually the residuals are good, that the distribution is reasonable, then we do the test. Do not focus only on the significance of the slope. Try to use the data together. Okay? Sometimes we can find poor regression that are statistically significant, which can be, but if the regression is poor, it's poor. I had a teacher of statistics that was telling me this regression is bad, not by chance, it's really bad, because statistically it's really like this. So try to have a global idea of what we are doing. And remember this, when we are doing analysis of means, what we can do in any case is to approximate a regression line. This is the first line of the Anova table that appears when we do the analysis with SPSS. No? There is a first line talking about model and intercept. So it's telling us if the regression model between the means that we are analyzing is significant or not, and what is the coefficient of this regression. This information is passed also when you run Anova. Of course, having a regression between two sets of data is not the same of having a regression between a good distribution of data. So if you really want to develop a model for the prediction, this would be the best situation. If you cannot, because your data are not well distributed, then you can go back and you can find another kind of model with all the limitations related to this model. But at least you can say, okay, it's supposed to be something like this. So Anova or regression, well, it really depends by what we want to do. there is not something that is better. It's really related to the question. If I know from the beginning that my point is find differences between groups, answer one question which is yes or no, significant hypothesis or null hypothesis, well, then maybe it's better to look for ANOVA and then extrapolate a regression if I really need it. If I know that my aim is actually looking for a causal relationship between two factors, between two variables that I'm measuring, well, then maybe I want to work with the regression, but I need to verify that the distribution is good enough. There are other tools that we are not seeing here, but that you should be aware that they exist, and are chi-square analysis and logistic regression. So we have seen ANOVA and regression analysis. We can mainly split it like this. If the independent variable is categorical and the dependent variable is continuous, then we use ANOVA. If they are both continuous, then we use regression. If the dependent variable is categorical and the independent is continuous, then we can use a logistic regression and make a classification. If my subjects are taller than 1 meter and 60, I classify them as tall. If they are shorter, I classify them as short. The dependent is categorical, tall, short. The independent is continuous. Or the case in which they are both categorical, and we can run what is called the chi-square. Okay. They are all related, and they all work with sum of squares somehow in different ways. We are not going through these two, but with the knowledge you have acquired in this course, if you need to study them, you should be able to do it. Final, take-home message. We are trying to find information related to some physical realities that we want to study. Okay, so we have information related to the dependent variable and the independent variable, and we want to see if these information are somehow related. So what we are really interested in is the mutual information that puts the two things together. Don't make the error to look for a lot of information, more data, more variables. This does not mean that your result will be better, because if you have a huge amount of information but you have no mutual information, then you're losing everything. It's much better sometimes to have less information, less variable, really related to the thing that you want to study, and you can find much more mutual information that can help you to see if these two things are related. More data is not automatically the answer. More valuable data, yes. Questions? Curiosity? Glass of water? No? Then see you next trimester.